of the column are hinged. Right? Write that line. So there are, as I said here, total 4 derivations are there with different end conditions. For your examination, there will be one derivation. Okay, out of 4, there will be one derivation given in your examination most of the times. Okay. So understand all the derivations clearly. If you get any doubt in between during the explanation, you can interrupt and you can ask the doubts. Okay. Now write the first case, expression for buckling load or crippling load when both the ends of the column are hinged. Okay, we'll derive the equation for the buckling load or the crippling load when both the ends of the column are hinged. Okay, this is the first case. Okay, now write the diagram for the same. Now initially the column will be straight. Now I will write deflected shape of the column. In the column is hinged at both of its ends. Okay. Write this diagram, all of you. This is what the deflected shape of the column. Okay, when the both the ends of the column are hinged. So this is the symbolic representation of hinge. Okay, and it is acted upon by the load P, axial load P. Okay, let us take L as length of the column, L as initial length of the column, L as initial length of the column. So you consider this as end A, this as end B. Okay. Now for derivation purpose, let us consider a point along the column at a distance x from end A. Okay, and corresponding deflection at a distance x. Let us take it as y. Okay, so this point we will call it as point C. Understood? For derivation purpose, I have considered a point at a distance x from the end A, and at a distance x, let us assume y is the deflection of the column. Okay, y is the deflection of the column. Okay, here also hinged. Both the ends of the column are hinged. If both the ends of the column are hinged, this is what the deflected shape means. It is concavity. Correct? It is concavity towards the center line of the column, towards the axis of the column. Correct? So concavity means plus sign or minus sign for concavity. I told sign conventions. If it is concavity towards the central line of the column, whether it is a sign plus or minus. Anyone can answer? Plus or minus it is. Just look here. Sign convention. Concavity means the sign is negative. Sign is negative. Okay. Now Now initially we will find the moment due to crippling load about the point C. About the point C. Okay. Below, right? Below, right? Moment due to crippling load is equal to crippling load means P only. P is the crippling load. Okay. Crippling load means it is a load at which the column start buckling. Okay, the column will undergo failure. That is called as crippling load. Okay, moment due to this crippling load. Okay, means at this point you have considered a point on the column, no? So about point C, what is the moment of this force P? About point C, what is the moment of force P? Anyone can tell the answer? Shreyas, what is the moment of force P about point C? Shreyas,
Sir,
what is the moment of force P about point C? P into
L minus X.
P into
L minus X.
how it is L minus X? See, perpendicular distance of the point C from the line of action of force P. Which is the distance that you need to take? Perpendicular distance. So this is the line of action. The vertical line, vertical dotted line is the line of action. You have to take perpendicular distance of point C from the line of action. Which is the perpendicular distance?
Y.
Y. So P into Y. Correct?
Yes.
So moment due to crippling load is P into Y. What about the sign, plus or minus? Sign. You have taken moment about C, no? P into Y you got. Sign, plus or minus. Here you see sign convention. Concave, if it is concavity, negative sign, convexity, positive sign. Now look into the diagram. Tell me the sign.
Negative.
Plus,
Negative, sir.
yes, negative. Okay. If it is concavity, then it is negative. If it is convexity towards the center line, then it is positive. So here it is, the column is concavity towards the center line. Therefore, the sign is negative. Okay. Therefore, M is equal to moment due to crippling load is equal to minus Py. So we know equation for the same moment in terms of the deflection of the beam, that is M is equal to EI into d square y by dx square. Okay, you are all familiar with this particular equation, correct? So in Mechale's method, I have explained this. M is equal to EI into d square y by dx square. Okay. Now M is equal to minus Py is there. One more equation we have, M is equal to EI into d square y by dx square. From both the equations, we can write, therefore EI into d square y by dx square is equal to minus P into y. Okay, minus P into y. Therefore EI into d square y by dx square plus Py is equal to 0. I have brought that RHS term to the LHS. Okay. Now dividing by EI, you will get d square y by dx square plus d square y by dx square plus P by EI into y is equal to 0. Okay. Now we have got a differential equation. Okay. We have got a second order differential equation in terms of y. Correct. Now for the solution of this differential equation is below, right? The solution of above differential above differential equation is right below y is equal to C1 cos x root P by EI plus C2 sin x root P by EI. C2 sin x root P by EI. Okay, call it as equation number 1. Okay, so no need to show the detailed calculation for this solution of the differential equation. Okay, you need to remember this solution, students. Okay, you need to remember not only for this derivation, for all the derivation, for all the 4 derivations. Like this, the solution will be directly written. You need to remember these solutions. Okay, if you go on finding the solution, the calculation becomes lengthier. Okay, you need to remember. And all the solutions for different cases here, they are almost similar to one another. There is minor difference in the equation that you need to remember. Okay, the solution of the above equation is equal to y is equal to C1 cos x root P by EI plus C2 sin x root P by EI, where below, right, where C1 and C2 are constants of integration. C1 and C2 are constants of integration that we need to find by applying what? Boundary conditions that you used to follow in Michaelis method. The same procedure. Okay, after writing the solution, we will get the constants. Okay, constants. These constants should be determined by applying the suitable boundary conditions. Okay, now write the centered line boundary conditions. To get the values of C1 and C2, we are applying the boundary conditions. Boundary conditions. Okay. Now coming to the boundary conditions, here look into the figure or the deflected shape of the column or buckled shape of the column. Here you can see, students, see x is considered from point A. Okay, this x distance is considered from point A. When x equal to 0, when x equal to 0 means at point A. When x equal to 0, what is the deflection? What is the value of deflection? When x equal to 0, what is the deflection value? Please be interactive. Tell the answer whether it is right or wrong. Tell the answer. What will be the deflection at x equal to 0? Bonus ray. Bonus ray.
So y is 0, sir.
Y is equal to. Tell the answer.
Y is 0, sir.
0 only. There is no deflection. No, at the point A, there is no deflection of the column. Deflection is 0. At x equal to 0, y equal to 0. So this is one of the boundary condition. And second boundary condition, at x equal to L. Okay, that x is considered from point A. Okay, so to point B, x becomes equal to L. At x equal to L, what about the deflection at point B? Again, what is the deflection at point B? What is the deflection at point B?
0, sir.
0. Here also the deflection is 0. So we need to utilize these two boundary conditions to get to solve for the integration constants C1 and C2. Now I'll take the first boundary condition. I'll take the first boundary condition. First boundary condition, that is at x equal to 0, the corresponding deflection y equal to 0. So in the equation 1, you substitute x equal to 0 and y equal to 0, you will get the value of one of the constant. value of one of the constant. Please solve and tell me the answer, whatever you get. Okay. I'll give 1 minute time.
C1 is 0, sir.
Huh?
C1
C1
is
is 0.
0.
You'll get C1 equal to 0. Now apply the second condition. Apply the second condition and solve. If I apply the first boundary condition, you will get C1 equal to 0. That is right. Here in the equation 1, we have to substitute y equal to 0 and x equal to 0. Y equal to 0 is equal to C1 cos 0. Cos x means there we have to substitute 0 plus C2 sin 0. Correct? So this value is 0 only. Therefore, cos 0 value is 1. Therefore, C1 becomes equal to 0. Okay. So by applying the first boundary condition, we got the value of C1, that is 0. Go for applying the next boundary condition, that is at x is equal to L. At x equal to L, again the deflection y equal to 0. Substitute x equal to L and y equal to 0 in equation 1 again. 0 is equal to C1 cos L root P by EI, okay, plus C2 sin L root P by EI. Okay, now we know the value of C1, correct? C1 equal to 0, so this term becomes 0 because value of C1 equal to 0, correct? Now the remaining term is, C2 sin, correct? C2 sin L root P by EI is equal to 0. Is equal to 0. Now from this equation, either C2 equal to 0, okay, from above equation, either C2 must be equal to 0 or the value of sin L root P by EI must be equal to 0. Correct? So there is product of two terms. C2 is one term and sin L root P by EI is another term. Okay. The RHS to become 0, either C2 must be equal to 0 or sin L root P by EI must be equal to 0. Okay. Now here in these two equations, okay, in these two equations we have to choose the correct equation. We have to choose the correct equation. Correct equation means, see, if C2 becomes equal to 0, no, assume that C2 is 0. If C2 becomes equal to 0, okay, C1 is already 0, correct? C1 is already 0. If C2 is also becomes equal to 0, then deflection y becomes 0 only, which represents that there is no deflection to the column only. Am I right? C1 is already 0 by applying the first boundary condition. If you substitute C2 is also equal to 0, there is no equation for the y. There is no deflection only. Okay, which represents that, which indicates that there is no deflection to the column only. Okay, which is practically not applicable. Therefore, C2 cannot be equal to 0. Okay, by considering the practical aspect, C2 cannot be equal to 0, but sin L root Pi can become 0. Okay, therefore, let us take the second correct condition. Therefore, sin taking or considering sin L root P by EI is equal to 0. Okay. Now, sin L root P by equal to 0. If the RHS to become 0, what should be the value of the bracket term? Okay. When the sin value is 0, when the sin value is 0, sin 0 is 0, correct? Sin pi is 0, am I right? Sin 2 pi is 0 or sin 3 pi is 0 and so on. Okay. Therefore, sin L root P by EI is equal to either sin 0 or sin pi or sin 2 pi and so on. Okay. Therefore, the value of this bracket term, okay, therefore, the value of this bracket term will be equal to L root of P by EI is equal to either it may be 0 or pi or it may be 2 pi or 3 pi and so on. It may be any value. Okay. So when the bracket term is either 0, pi or 2 pi, then only you will get the RHS 0 here. Okay. Now you need to consider the least practical value. You need to consider least practical value. So means here we can see students, L is nothing but length of the column, P is crippling load, E is Young's modulus, I is moment of inertia. Okay. You cannot take this 0. It has got some value. We will take the least practical value. Least practical value is nothing but what? Pi. Okay, we will take pi as suitable term for this L root P by EI. Therefore, taking least practical value, that is L root P by EI is equal to pi. L root P by EI is equal to pi, squaring on both sides. Squaring on both sides, we get L square P by EI is equal to pi square. Therefore, P is equal to pi square EI by L square, which is the equation for crippling load or buckling load of the column when both the ends of the column are hinged or pinned. Okay, so this completes the derivation. Do you have any doubts at any point of calculation here? Any doubts here in this derivation, students? Any doubts you can ask. I'll briefly explain the procedure once again or the derivation once again. See, we are interested to find the expression for crippling load of the column when both the ends of the column are hinged. Okay, when both the ends of the column are hinged, this is what the deflected shape of the column. Okay, for derivation purpose, we have considered a point at a distance x from point A and corresponding deflection at a distance x, we have considered it as y. Okay. So in the initial step, what we have done is we have determined moment of this crippling load P about point C. Okay. So moment is nothing but force into perpendicular distance. Force is P, perpendicular distance is Y, P into Y. So based on the sign convention, what we have here, it is concavity. For concavity, if the buckle shape is in the concavity shape, then the sign is negative. So negative sign I have taken minus P into Y. Okay. So we have known with the equation. Okay, we are familiar with one of the equation for the moment, generalized equation for the moment, that is m is equal to EI into d square y by dx square. Correct. So from first and second equations, we can equate RHS of both the equations, that is EI into d square y by dx square is equal to minus Py. I have taken minus Py to the LHS, so it became EI into d square y by dx square plus Py equal to 0. And dividing the whole equation by EI, we got d square y by dx square plus P by EI into y equal to 0. So we got a differential equation. And the solution of the differential equation I have written. That is y is equal to C1 cos x root P by EI plus C2 sin x root P by EI. Now we got the two integration constants C1 and C2 that can be or that should be determined by using the boundary conditions. And I have explained the boundary condition that at x equal to 0, at x equal to 0, the deflection y equal to 0, and at point B, which means x equal to L, the deflection is equal to 0. By utilizing these two boundary conditions, we are able to find the constant C1 and C2. By applying the first boundary condition, means by substituting x equal to 0 and y equal to 0 in this equation 1, okay, we got the value of C1 as 0. Next, applying the second boundary condition, that is at x equal to L, y equal to 0, means we have substituted x equal to L and y equal to 0 in equation 1. So we got this equation. We got this equation. As C1 value, we already got 0. This term will get cancelled. Okay, only the remaining term is C2 sin L root P by equal to 0. Okay, so from the above equation, there are two terms. One is C2 and another term is sin of L root P by EI. Either C2 should be equal to 0 or sin L root P by should be equal to 0. Okay, for this RHS to become 0, correct? So C2 cannot be equal to 0 because if you substitute C2 equal to 0 here, C1 is already 0. Okay, C2 also becomes 0 means there is no equation for the deflection of the column only. Okay, which practically says that there is no deflection of the column only. Okay, that is practically not applicable. Therefore, C2 cannot be equal to 0, but the remaining term sin L root P by EI can become 0. Therefore, I have considered the second condition, this condition for the next calculation, that is sin L root P by equal to 0. To become sin L root P by equal to 0, in the RHS, we must have either sin 0, pi, sin 2 pi, sin 3 pi, like that, so on, sin n pi. Okay. Therefore, the bracket term L root P by must be equal to 0 or pi or 2 pi and so on up to n pi. Okay. Considering the least practical value, that is pi, the first value, the L root P by equal to pi, squaring on both sides, we got, and simplifying, we got the expression for the buckling load or the crippling load for the column when the both ends are hinged. That is P is equal to pi square EI by L square. Okay, students. Any doubts here? Any doubts you have? Okay, thank you.